All my camera's working today.
Weren't we like 20 people in this class like a week ago?
What's that?
Weren't we like 20 people in this class about a week ago?
So I'm not sure what you're asking. Are you asking, did we have more people in the Zoom sessions before? Is that what you're asking?
There used to be a lot more people in the Zoom sessions.
It kind of fluctuates, you know. I think it just depends. Like today's not too bad. I don't know. I would probably say there maybe like 12-ish, you know, on a decent day, and that's pretty average. That's actually what most you know, people have. Most instructors have. I don't know. I guess people watch them later, or they don't watch it at all. I don't know. Yeah. Okay, so why don't we begin? Do we have any questions before we get started on anything? Now, you guys know what I'm going to ask, right? Can you please turn on
Video.
video? There you go. You got it. That's right. It helps a lot. Trust me. Lecturing to black screens is really depressing. I think studies have shown. Okay, so what we want to do today, and this is actually going to be a pretty easy section. So, you know, if you've been behind and you want to catch up, now's actually a really good time to catch up. So what we're going to do this week is we're going to add to our list of derivative results. So we've been talking in this class about forms and formulas. And up to this point, we have two forms, right? We know how to take the derivative of a sum and the derivative of a number times a function, okay? So our first form said, if we wanted to take the derivative, right, that's what that prime means, for the sum of two functions, it's the sum of the derivatives of the functions. Provided, of course, the derivatives exist, right? There's that caveat, obviously. And so sometimes when people write this in operator notation, and I'm going to erase this in a minute, but just to kind of illustrate, what they say is they say that the derivative operator, which is what this is, it distributes across the sum. And so if you wanted to write this using operator or you know, Leibniz notation, you would write it like this. Okay. All right. The other formula we had the formula for the derivative of a number. So C here is just a number times a function. And we said it was the number times the derivative of the function. Okay. And again, if I looked at this in operator notation, right, what it says is it says that scalar multiples factor out of derivatives. All right. And we call these forms because this is true regardless of the type of function we're looking at. Okay. This could be a power function, an exponential function, a trig function, whatever. Okay. But then we also had formulas. And lucky for you, you only have one formula that you have to remember. If you were in 241, you'd have a bunch of them. And the only formula we have is for power functions. And so we've been spending the last 2 weeks really talking about this rule, right? Called the quote-unquote power rule. Now, one quick comment that you should know is that most likely from this point on, I'm going to generally use the prime notation as opposed to the DDX or the operator notation, And the reason why is it's much easier to write. It's very, very compact, okay? Later on, we're going to talk a little bit about prime notation and a few things we have to watch when we're working with it, but that's what we're going to use. I'm not going to use operator notation, okay? Just because it's so nice and compact. So today we want to add to this list. We want to add 2 more forms. And the first is the form for the product of 2 functions. So here I have a product of 2 functions, some function f times some function g. One quick thing to note really briefly, notice that when I'm writing functions, I'm not writing this, okay? You know, I'm not writing f of x, okay? When we're using letters like f, g, and h, it's completely understood we're talking about functions, okay? So again, this is a little bit of shorthand, all right? And so what this rule says, if you take the derivative of a product, the way that we get that is we take the derivative of the first function, we leave the second function alone. Okay, so I have a product, and the first factor is the derivative of the function, one of the functions. I leave the other function alone, and then I have a second term where now I leave the first function alone, and I multiply it by the derivative of the second. And people call this the product rule. For obvious reasons. So is everybody good with what I'm writing? You can read it and understand that? Is that okay?
Yep.
Okay. Now, if you think about it, what we're really doing is we're learning how to take the derivative of algebraic combinations of functions, okay? So I know what to do when I'm adding them, when I'm multiplying them by a number, when I'm multiplying them together. The only one we haven't done is what? Quotients, right? What happens when I divide another function by another? One function by another. So here I'm going to have some quotient. A quotient is just a ratio, right? And I want to take its derivative. And the question is, how do I do that? And so this is going to be another quotient. On the bottom, I'm going to put g squared. And in the numerator, I'm going to put something that looks like the product rule with one difference. I'm going to subtract these 2 terms. So I'm going to have an f prime and a g, and an f and a g prime, but I'm going to subtract them. And so you notice that there's one big difference between the product and the quotient rule. In the product rule, it doesn't matter the order in which I put these 2 terms, because in a product, it doesn't matter the order in which 2 things are multiplied. 2 times 3 is the same as 3 times 2, right? And so this should be the case. We totally expect this. In the quotient rule, the order matters. Okay, so you know the derivative of the function in the numerator has to come first. Otherwise, you'll get the sign wrong. And you probably watched in the video, there are little mnemonic ways of remembering this. So this is called the quotient rule. Again, for obvious reasons. And one of the ways that people remember this is they remember this as low d high minus high d low over low squared, okay? I think it's a waste of time remembering that, but some people like that, okay? So low d high, meaning that this is the low function, the one on the bottom, times the derivative of the high function, the one on top, minus high d low. over, rho squared. I think it's easier to remember that than that, but And the reason why is, the reason why I don't like this mnemonic, I'll tell you why very quickly, is because students tend to misremember it. They tend to remember it for some reason, I don't know why, as high v low. And right there, you're already, off the tracks if you're saying that, okay? All right, good. Any questions on the formulas, what we're writing, what the symbols mean? Everybody's good with this so far? I have a little bit of glare going on the bottom. Here, let me move this. A little better. Nope, it just moved the glare. I know how I have to move it. Hold on. Okay, let's try that. There, that's better. Okay, good. And so what we're going to do this week is we're just going to focus on these two rules. And you're going to find, quite frankly, if you know the power rule well, you're going to find that this is a very easy module to go through. It's not a lot of work, okay? What will really screw people up, two things I can tell you right now, is A, not knowing how to use the power rule, especially when you have roots and reciprocal powers, right? You have to do something special to put it in this form. And the other is just the arithmetic, okay? And I'll talk a little bit about bookkeeping methods so that you don't make stupid arithmetic errors. All right. Anything we want to talk about, though, before we go on? I just want to make sure we're all on the same page. Everything is good. Okay. So I'm going to erase this, and we're going to work some problems and see how to do this. As I'm working the problem, I'm going to try to show you how to set it up so that even if you do make an error somewhere along the way, you won't lose points, okay? So let's look at the product rule. And we will write out what that is again. It says that the derivative of a product is the derivative of the first term times the second plus the first term times the derivative of the second. And there aren't a lot of formulas you should remember, but all of those formulas that I gave for the forms and the formulas, you should remember, but there's only, what, 5 of them, right? And you use them so much that it kind of becomes second nature, right? Okay, so let's look at the first one. So for all of these, we're going to find the derivative of the following functions. Okay, so for the first one, I'm going to define some function f of x as x plus 1 times 3x minus 5. And let's use our quotient rule, okay? So this is like my first function. And by the way, I'll mention really quickly, some people write this rule like this, okay? Because notice, I want to say this is like f and this is like g, but I can't say this, right? Because I defined this product as f times g. So sometimes people write it like this. U times v is u prime v plus u times v prime. I don't like doing that because U's and V's look a lot alike, okay, especially with my handwriting, but some people do it like this. Okay, so the product rule tells us, and here's the first hack, okay? You're on an exam, you're working this problem. Notice that this thing is kind of complicated, pretty easy to make a mistake. The first thing to do is to write out this rule. So what I mean by that is I'm going to just say that the derivative of f is, and I'm not going to worry about taking the derivative of the first term, okay? I'm just going to write it as x plus 1 derivative of, okay, times 3x minus 5 plus x plus 1 times the derivative of the quantity 3x minus 5. And there's a reason why you want to do this, okay? When you're looking through your work and you're checking it, I think you're going to find that if you write it out this way, the check will be much easier, okay? So now I'm just going to go ahead, I'm going to take the derivative of each of these. So the derivative of x plus 1 is, let's see, who wants to be a victim? I mean, a volunteer. Derivative of x plus 1.
One.
It's just going to be 1. And again, you know, if you're not sure, you can always work this out on the side, okay? Derivative of x plus 1, what do I know? I have the derivative of a sum. So it's the sum of the derivatives, right? And we know that this is 1 using my power rule, and this is 0. Okay, good. So I'm going to write this like this. And of course, we didn't do anything to the second function, okay? And for the second term, we didn't do anything to the first function. And I'm going to do the same thing, right? Take the derivative of 3x minus 5. And now for the $12 million prize and the year's worth of total wax, what do we get? Give that man a cigar, free. Notice also how easy this is going to be to check your work, right? You know, you're going through the exam, okay, I have a product, yeah, I used the product rule correctly, did I take the derivative of that? And you can see it, right? I mean, if you have some facility doing this, okay, makes it much easier. And now I'm just going to simplify. I'm done. I've taken the derivative, right? This is now the function. This is no longer my original function. This is the function that's the derivative of this function. And now I'm just going to go ahead, distribute, and simplify, right? Distribute 1 across, nothing to do, right? And then I'm going to distribute my 3 here. So I'll get plus 3x plus 3. And finally, I'm going to combine my like terms, right? 6x minus 5 plus 3 minus 2. Again, you know, when you're on an exam, and I do this myself, okay? I've been doing algebra, quite frankly, longer than you guys have been alive, okay? But when I simplify things and I want to be careful, okay, I have a kind of bookkeeping technique, okay? I say, okay, these are like terms. Notice I have like terms marked the same way. And if I want to go back and check my work, it's much easier, okay? Did I get all the x for the first terms? Yep. They add up to 6x, okay? And that's our answer. Now, what I want to do is I want to do it another way. But before I do it, is everyone good with this, what we've done so far? Everybody tracking? Okay. Okay, so what I want to do to convince you this is not a figment of my crazed imagination is I want to expand this out and then take the derivative of the expanded function, okay? So if I go ahead and expand this out, right, I'll get a 3x squared. And I'll get a minus 5x and a positive 2x, right? And I'll get a minus 5 for the constant term. And you can see if I go ahead and do my check, right, that the derivative of f of x is the derivative of 3x squared minus 2x minus 5. And when we work that out, we can see what we'll get, right? Take the derivative of the 3x squared term, the 2 will come down. 2 times 3 is 6x minus 2. And we get the same answer. And they may ask you on an exam, although I don't know how they can really check it, short of you submitting your work, but they may ask you to show it both ways. To show that you know how to use the product rule, but then you can also check yourself too, which is nice. Okay? See, I told you it was simple, right? Okay, so let's look at one that's maybe a little harder now. We'll just keep on kind of ratcheting up the level of complexity. I'll make something different. So we'll say yx is x cubed minus 4x times 4x minus 1. So first step, we want to use the product rule. So this tells us that y prime of x is equal to the derivative of the first function, leaving the second one alone, plus the first function times the derivative of the first. The second. Okay, that's what the product rule tells us. And so now we're going to take the derivative of each of the individual functions. And, again, you want to try to get to the point, I think, where you can do this in your head, all right? If you have a hard time with that, though, you can always go off to the side and do it, right? And use your rules for the forms. Okay, so here for the first one, I'm going to get, who wants to tell me what the first one is? And we'll pick on somebody new. Let's see, Cassandra, you want to help us out? What are we going to get for the derivative of our first function here?
We're looking at the very first one.
Mm-hmm.
Can you hear me?
I can hear you, yeah.
Okay. Let's see, is it 2x to the second? So you subtract 2.
Okay, so let's see. So here's what our power rule says. We have a power function, right? And our power function says we're going to bring down the exponent and reduce it by 1. So I like that exponent of 2 you have, right? That I think is going to be okay. So I'm going to have x to the third. And when I look at this guy, just like you said, that's going to be x to the 3 minus 1 or 2. But what's going to be out in front here?
3.
Bingo. Perfect. All right. So we get the 3x squared, and are we done?
No. So,
okay. And then so what else do we have?
4.
Okay, and a minus 4. Now, one thing to be careful about, things that will screw you up on this problem. notice that I have a really complex expression here. Make liberal use of parentheses. So the one thing that students will do sometimes on an exam is they'll like leave out something like this, okay? And that will kill you. I mean, if nothing else, just in terms of partial credit. It makes it really hard to start to follow your work. Okay, and of course nothing happens with this other term, so we just leave on B, and you get x cubed minus 4x. And then we take the derivative of 4x minus 1. Well, we actually kind of already did that problem, right? We know how to take the derivative of a number times a function, so we're just going to get 4. Does that look okay? Does that seem all right?
Yes.
Alrighty then. So now we're done. So now all you have to do is just go ahead and FOIL and simplify, okay? See how simple it is? And again, the one thing that I want to impress upon you, and this is important, is that writing things out will help you a lot as far as extra credit. Where students lose points, and this is an easy problem, as far as what you're going to see on the exam. You don't want to miss a problem like this, okay? But what will really screw students up is they'll try to do everything in their head and just write out the answer. And sometimes it works, but sometimes it doesn't. And on an exam, you don't want something that sometimes works and sometimes doesn't, right? So if you do this intermediate step, even if you make a dumb error in this next step, this last step, I'll at least know that you knew the main part, and you just screwed up the algebra, which isn't that big a deal, right? Because this isn't a class on algebra. Okay, now I'm just going to go ahead and distribute here. And so, so one of the things I emphasize a lot in classes, I think it's just important in general when you're doing math, is you want to have a plan, okay? So again, when I'm multiplying, I want to keep track of everything, okay? Bookkeeping. So this first product is 12x squared, okay? When I hit 3x squared or multiply it by minus 1, I get a minus 3x squared, and I've used those up. So
isn't that 12x cubed?
Whoops. You caught me. 12x cubed, thank you. Yeah. Now see, that's a perfect example. If you did that on the exam, you wouldn't get penalized a lot. So. Okay. There you go. Right. So we've
I did
done
the
all
exact
these.
same thing at first.
See, it must be contagious, right? Okay, and then if I go ahead now and I multiply the minus 4 through right, I get minus 16x. Keep an eye on me here. And then finally, minus 4 times minus 1 is 4. So it's really kind of good to have these bookkeeping methods, all right? Multiply the x cubes, 4x cubed, and I can just write in below here, right? And then multiply here, minus 16x. And when you do it this way, that way you make sure you've hit all the terms and everything's okay. Makes it easy to check when you're going through. And now I just do my addition. And I'm going to get 16x cubed minus 3x squared minus 32x plus 4. Okay? And that's our answer. So the thing that kills people really is just the organization and the algebra. And that's why having a plan, knowing how to lay things out, and having some way of doing algebraic bookkeeping will really save you a lot of headaches and trouble. Okay. So everything look okay there? Are we all good?
Yep.
And if I wanted to, and so one thing that students sometimes say is they say, well, I don't really see that it's that much of an advantage. because I could have foiled this through. I mean, I have to do a lot of foiling anyhow, right? In fact, I have to foil twice here. Here I only really have to foil once, okay? So sometimes people say, oh, you could have just foiled it once and it would be easier to do. And for this problem, you're probably right. But trust me, there are problems where you definitely want to use the product rule. But let's just go ahead and check and make sure. And by the way, I'll mention, you know, doing this on the exam, you should have more than enough time. Doing this check on the exam is good because I would have been able to catch that mistake. Always having a way of independently verifying your results or checking it is a good thing. Okay, so if I FOIL, right, I'm going to have a 4x to the fourth, right? And then I'm going to have a minus x cubed. And then I'm going to have a minus 16x squared. And finally, I'll have a positive 4x. And so let's see if we got the right answer, because we can do this pretty much by observation, right? And let's see, I will, I'm gonna pick on Cassandra again. Let's make sure we got the power rule down. What will I get for the first term?
16x to the third.
Bingo, good. So now you know you got that down. Second term, okay, minus 3x squared. All right, so far we're doing great. Minus 32x plus 4. You done good. Okay. So now I know on an exam, I don't have to wonder, did I get it right? The chances of me making an error with two independent methods is minuscule. Okay. Any steps that we want to go over here or talk about maybe a little bit? We have the time, trust me. You know, a lot of times students say to me, they say, they'll have a problem. They'll say, well, why didn't you say something in class? Oh, well, I don't want to interrupt class. This is the whole point of class. This is why we're meeting in person and we're not doing a video. So you can ask questions, okay? Everybody's good?
Yeah, so far.
Okay. So on Wednesday, we're going to do more practice problems with the product rule. Most likely I'll go through the handout sheet. Friday, to be honest, we're going to probably finish the material earlier. So Friday, I'm probably going to show up, and if you have any questions, great. And if you don't, then we will call it a class. Because really, this material, once you understand the power rule, really is pretty straightforward. So let me go ahead. I want to do a few problems with the quotient rule. And so on Wednesday, what we're going to do is I'm going to do more complicated problems. What could you see in this problem that would have made it more complicated? How could I have made this problem more complicated?
Using fractions, stuff like that.
So that's an excellent point, and I'm actually going to go through one where there is a fraction. If I had fractions, what else could you see that would make this hard?
Square root.
Negative exponent.
Yeah, I didn't have any with reciprocal powers. I didn't have any with roots. Okay, and so on Wednesday we're going to look at those types of problems, and then you guys will be masters of the product rule and the quotient rule. All right, good. Do you guys ever wonder where these things come from? Or not? I'm just kind of curious.
Not really.
Meaning how the product rule is derived, or?
Yeah, exactly. That's what I'm getting at.
Not really.
Okay.
But it makes sense though.
So
Evaluating the slopes.
So you actually can, yeah, you actually can derive it. I'll show you very, very quickly, okay? I'll make it each. So if you have, if you actually want to evaluate or you want to prove this formula, you have to evaluate this limit, right? So this is like the function at x plus h minus the function at x all over top of h. All right. And when you do that, there's a little trick you have to do that. When you do that, you end up showing that this is exactly what you get. And the trick is that you have to add and subtract a few things. That's okay. That's okay. I won't bother you with it. But there's a little algebraic trick where you add and subtract the same thing, and you can end up sorting things out, and you end up getting. But this comes from the definition of limit, right? This is the limit. This is the definition of the limit of a function. Right? It's going to be, if you call it something rather than f and g, I'll call it maybe v. This is actually the limit definition of the derivative, and that's how we get it. Okay. All right, so let's do a few problems with the quotient rule. And so our quotient rule says that if we're taking the derivative of a fraction of functions, it looks a little bit like the product rule, but there's a negative, and then we have to divide by g squared. If you look at books online or you look at Wikipedia or whatever, they tend to use, again, these functions u and v. Okay, so you'll see something that looks like this. And when I was a student, back when the dinosaurs roamed the earth, that's the notation that we use. Okay, so let's look at a few problems. Let's see, number 3 now? Let's look at the derivative of now, one of the things that you want to do is you want to realize when to use the quotient rule and when not to. You might say this is a good product for the quotient rule, but it's actually not. This is the problem where we shouldn't use the quotient rule. Let me put up here, okay. You can use it, but you shouldn't use it. Let me put it like that. And you might say, Matt, that's stupid, because you just told us if we have the derivative of a ratio of functions, we can take the derivative. But why is this? Why shouldn't we use the quotient rule here? Anyone know? Is there a simpler way? Yeah.
Just bring the negative exponent to the top.
Okay, you can do that.
Or bring the exponent to the top and make a negative.
I can do that. I'm thinking of something, and if you did it the right way algebraically, you would see what I'm saying. I'm thinking of something a little easier than that, though. So here's kind of the point that I want you guys to see. So normally we use this identity in this direction, right? If we have two quantities over a common denominator, we can add the numerators. However, it works the other way too, right? It's an identity, okay? And so what I'm going to do is I'm going to first break up this fraction. Okay? See, nothing up my sleeves, right? And now I can use the fact that I can get cancellation. So I'm going to have 2 factors of x here, which are going to cancel out with 2 factors of x on the bottom. And I'm going to have 1 factor of x that's going to cancel out on both. All right. Okay, what am I going to do next?
Bring them to the top and then derive them.
Exactly.
Separately.
Exactly. Now I'm going to realize I have power functions in disguise, right? These are really power functions, reciprocal powers. So now I'm going to write this as x to the minus 3 plus 2 times x to the minus 4th. And I can do this properly. These are now power functions, right? And I go ahead and do those, and I get minus 3 x to the minus 4th, right? And for this term, I bring down the minus 4 and multiply it by 2, and I reduce the exponent, and I have x to the minus 5th. And then, of course, I would go ahead and now I go backwards and write them as positive exponents, bringing them down in the denominator, okay? And there's a reason why I tell you this, and it's because when you start to get into things that become kind of complicated algebraically, this formula can involve a little bit of algebra. And I don't know about you, but I'm lazy, okay? I want to do it the simplest way. So I can simplify it like this, okay? And just take the derivative of power functions. I would much rather do that. All right. So now we know what our answer is. But let's go ahead and work it the other way. But this is purely for class. I don't want you to do this in general. Let's just convince ourselves we know how to do it, okay? Okay. So let's use the quotient rule, but again, you know, and if you were doing this on an exam, you want to do it this way, but just for the purpose of the class, right? So I'm going to go ahead, I'm going to apply the quotient rule. And let me go ahead well, I'm just going to leave it that way, that's okay. So the quotient rule tells me it's going to be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over top of the denominator squared. Okay? One of the things you'll see is that the setup for the quotient rule and the product rule are identical, right? First of all, we write down the rule, then what do next? We take the derivative of the individual functions, just like we did in the product rule, and then we simplify the algebra. Same 3 steps, right? So now we're going to go ahead, we're going to take the derivative of the individual functions. And so the first one, I'm going to get 2x plus 2. And of course, nothing happens with x to the 5th. Okay? And then I get minus x squared plus 2x. Nothing happens to the first function. And the second one, I bring it down, I'll get 5x to the 4th, right? Again, be very liberal with parentheses, okay? And then I'm going to go ahead and divide this by, what do I get when I square x to the 5th? Does anyone know?
X to the 7th.
X to the 7th, does that sound good? So here's some mathematical facts we're going to talk about today. If I have two things, a product of two things, and they're to the same base, I add the exponents, right? Because this means x multiplied by itself a times, this means x multiplied by itself b times. So how many times do I have x multiplying itself? A plus b times, okay? However, when I have this raised to a power, okay, it's equal to x to the a times b, all right? This is saying that you have b packets of x multiplied by itself a times, right? I mean, if we look at what we have here, x to the fifth squared, what does it mean to square anything? It means you multiply it by itself, right? So we have x to the fifth times x to the fifth. And what is that? That's x to the 10th. As advertised, right? 2 times 5. Okay? So you want to just make sure that you have those algebraic rules down pat. Okay, and now we go ahead and just distribute, right? Now we're just going to simplify. And so our final answer, when I distribute, right, I'm going to get 2x to the 6th plus 2x to the 5th. One of the things to be careful about here, okay, and this is again a kind of algebraic hump that students stumble over, is you have to realize that this minus sign multiplies this entire thing, okay? So if I was doing this on an exam, I'd make sure that I put a minus sign and then put this little parenthesis here, telling me that I'm taking the negative of everything in that parenthesis, right? And we go ahead and we do the math. You get, what, 5x to the 6th, and then finally 10x to the 5th. All over, see where these parentheses are coming in, right? All over x to the 10th. All right? And now we just simplify. We just combine like terms, right? So 2x to the 6th and minus 5x to the 6th is going to give me a minus 3x to the 6th. 2x to the 5th, and again, this is a minus, right? Because this minus sign distributes and it hits each of these terms, right? So I have 2 minus 10, which is minus 8x to the 5th over x to the 10th. And there's a number of different ways you can write this, okay? And this is where you're going to have to be a little careful, okay? Because I don't know exactly, different books have different conventions, okay? Notice one thing I could do is I could split this back up again, like I did in the beginning, right? What I'm going to do here is I'm going to take out the greatest common factor. What is the greatest common factor here? What is the factor that goes into all of these terms?
X to the 5th.
X to the 5th, thank you, right? X to the 5th divides into this term, divides into this term, divides into this term, okay? If you're not sure, just work it out. I mean, So if I take out an x to the 5th, I'll have minus 3x minus 8, right? I can check myself by distributing, okay? And if I factor in x to the 5th out of x to the 10th, I'll just have x to the 5th left over, okay? And these guys will cancel. And cold-bloodedly set it up that way. And now I have my final answer. What most people do, you don't have to do this, I'm just telling you this because this is probably how you're going to see the answer, okay? most people in math, when they have a negative sign multiplying every term, they bring the negative sign out in front. And that's what I'm going to do. I'm going to factor out a -1, okay? And then divide by x to the 5th. And that is our final answer. And if you go back and check it with what I did many moons ago, you'll find out we get the same thing, okay? Questions. Everybody's good. Okay. So Wednesday we'll pick back up. I'm going to do more complicated problems. And then Friday we'll just do, you know, a gemish. But chances are by Wednesday, we'll probably have all the material covered. All right. So, okay, that's all for today. I'll post the video later on this evening. If you have any questions, feel free to ask. If not, have fun.
Thank you.
All right, thanks, guys.
I wanted to talk for a second. Sorry.
Yeah, what's up?
I'm sure you're probably already aware of problem 12 on the homework.
So here's what we do, and this will save us a lot of time. Just go ahead and post it on the Google Sheets, and that way I look every evening and I'll check it out and make sure. And if it isn't, that way I can also get right back to you too.
Where's that at again? On
If you
our
go,
Canvas?
yeah, if you go to our Canvas homepage, here I'll show you really quick. Let me pull it up here. So if you go to our Canvas homepage, it should be right
there it
in
is.
front.
Google Sheet reporting errors.
Yeah. Just go ahead and click on that, put that in, and that will save us. That'll save us both time, and I'll check it over. And I mean, most of the time it is a mistake, but if it isn't, then I can also get back to you and let you know.
Okay. Also, there isn't really an excuse for this. I just kind of like let this go on accident last night, but on the I forget. It's not the rate of change homework. It was the other homework we had due last night. It was the tangent lines homework. I just did it a few minutes late. I kind of got behind, and my dad called me, and we were on the phone for a while, and I just didn't really pay attention to the time. But I got 100 on it, but it's marked as late.
Do me a favor. Send me a quick email, because right now I'm between classes. And it will go in one ear and out the other. Send me an email and I can look at it. I think I can fix that. Shouldn't be a problem. Those things happen.
Yes, sir. And then also one other thing. I don't know if you just haven't got around to grading it, but I think I still have a 0 in for the ground speed that we did. Because if you remember from the first week of class, I got kicked out and then joined back in and then kicked out and then had to join again. So both the ground speed and the vector introduction homework that we have, I think I still have a 0 in for it, but I turned it in. Already emailed you about it.
So yes, yeah. If you can put it all in the same email, that'll be good. And then when you, like I say, in the future, when you find problems, and you're going to find, again, this is going to be a common thing because we know that this program is not good and I can't go in and change it. So this is going to happen the rest of the semester, and so for that one we have an easy workaround. But yeah, send me an email about those last two things, the extension and about getting kicked out, and I can take care of that. Shouldn't be a problem.
Yes, sir. Thank you so much.
Good thing. Okay, good deal.
Have a good day.
You too. Talk to you later.
All right. Bye.
All right. There we are. That's what I'm.